Every year, nuclear power plants around the world quietly generate over 1/3 of their electricity from an element that didn't even exist on Earth before humans created it. It's heavier than lead, more toxic than almost anything else on the periodic table, and so radioactive that a piece the size of a grapefruit produces enough heat to warm your hands from across the room. It has powered spacecraft traveling beyond the edge of our solar system, and it sits at the center of the most destructive weapons ever built. But today, it's also one of the most important fuels in the future of clean energy. I'm talking about plutonium. And the story of how it's made is one of the most extraordinary journeys in all of modern science. Stay with me until the end, because what you're about to learn will completely change the way you think about the reactor powering your city. Unlike uranium, plutonium is not a naturally occurring element. With one exception, vanishingly small trace quantities found in uranium ore deposits, every atom of plutonium on Earth was manufactured, created, engineered into existence by human hands. That fact alone makes it unlike almost anything else we work with, and understanding it starts with a discovery made inside a single room at the University of California, Berkeley. On the night of February 23, 1941, a young chemist named Glenn Seaborg and his colleagues bombarded uranium atoms with deuterons, particles made of one proton and one neutron, using the university's 60-inch cyclotron particle accelerator. What came out was element 94, a new element that had never existed in any meaningful quantity on the face of the Earth. Seaborg named it plutonium, continuing the planetary naming convention that had given us uranium for Uranus and neptunium for Neptune. Pluto came next, the name stuck. Seaborg would go on to win the Nobel Prize in Chemistry in 1951, and the element seaborgium, number 106 on the periodic table, now bears his name. But on that February night, his team had only produced an amount so microscopic it was invisible to the naked eye. Less than a millionth of a gram, a trace so faint it could only be detected by the radiation it emitted. Within months, Seaborg's team discovered something that would reshape the entire trajectory of human history. Plutonium-239, one of its key isotopes, was fissile. Strike it with a slow neutron and the nucleus splits apart, releasing enormous energy and more neutrons that go on to split other atoms. A chain reaction? The same principle that powers every nuclear reactor on the planet, and the same principle behind the bomb dropped on Nagasaki in August 1945, which used plutonium rather than the enriched uranium of the Hiroshima device. The Manhattan Project scaled Seaborg's microscopic discovery up by a factor of 10 billion, what he later described as surely the greatest scale-up in the history of science, to produce enough plutonium-239 for the Fat Man weapon. To do it, they built massive reactors at the Hanford Engineering Works in Washington state, where uranium was irradiated in industrial quantities. The science of how that process works is still the foundation of plutonium production today. Here's what actually happens inside a nuclear reactor. The fuel, remember, is mostly uranium-238, the stable, non-reactive isotope that makes up over 99% of natural uranium. When uranium-235 atoms split during the chain reaction, they release 2 or 3 fast-moving neutrons. Most of those neutrons go on to split other uranium-235 atoms, sustaining the reaction. But occasionally, one of those neutrons collides with a uranium-238 atom, and instead of splitting it, gets absorbed. The uranium-238 nucleus captures the neutron, becoming uranium-239. That new isotope is unstable. Within minutes, it undergoes a process called beta decay, shedding a particle and transforming into neptunium-239. And then, within days, neptunium-239 undergoes beta decay again, transforming into plutonium-239. This happens continuously inside every operating nuclear reactor, whether the operators want it to or not. A single fuel assembly containing 264 rods after 3 years of operation will contain roughly 12.9 pounds of plutonium-239 locked inside the spent uranium pellets. Over 1/3 of the electricity generated in most nuclear power plants today actually comes from this plutonium, which fissions right there in the reactor core alongside the uranium-235 without anyone ever extracting it. The reactor is, in a very real sense, manufacturing its own fuel as it runs. But to use plutonium as a dedicated fuel source, you have to get it out, and that's where the science becomes extraordinary. Spent fuel rods are intensely radioactive, so hot in both the thermal and nuclear sense that they must be submerged in cooling pools for years before anyone can work with them. The pools glow with a faint blue light caused by Cherenkov radiation, energy released as charged particles travel through water faster than light moves through that same water. It is one of the most surreal and beautiful sights in all of industrial science. After cooling, the spent fuel rods travel to a reprocessing facility. There, robotic shearing machines cut the zirconium-clad rods into small fragments in chambers sealed behind thick concrete walls and operated entirely by remote control. The fragments are then submerged in concentrated nitric acid, which dissolves the uranium and plutonium while leaving the metal cladding behind. What emerges is a highly radioactive liquid solution containing uranium, plutonium, and hundreds of radioactive fission products. The separation step is called the Purex process, plutonium-uranium reduction extraction, and it's one of the most sophisticated chemical engineering systems ever developed. The liquid is mixed with an organic solvent called tributyl phosphate, diluted in dodecaine. This solvent has a specific chemical affinity for uranium and plutonium, drawing them out of the acidic water and into the organic phase while leaving the fission products behind in the liquid waste. The process is run through multiple cycles of separation and purification until the plutonium is isolated with extraordinary purity. When discharged from a reactor, spent fuel contains roughly 96% uranium, 1% plutonium, and 3% fission waste. The Purex process recovers nearly all of that plutonium and uranium, leaving behind only a fraction as high-level waste. The recovered plutonium emerges as plutonium nitrate solution, which is then chemically converted into plutonium dioxide, a fine, dark ceramic powder. It is at this point that the material enters one of the most tightly controlled manufacturing environments anywhere on Earth. Because plutonium dioxide is both radioactive and chemically toxic, every step of its handling takes place inside sealed glove boxes. Airtight enclosures fitted with thick rubber gloves built into the walls, allowing technicians to manipulate the material without any physical contact. The entire facility operates under negative air pressure, ensuring that if any containment breach occurs, air flows inward rather than carrying radioactive particles out. Workers are monitored continuously for radiation exposure. The plutonium itself emits alpha radiation, the least penetrating form, which cannot pass through the skin, but is profoundly dangerous if inhaled or ingested, even in microgram quantities. Inside those glove boxes, the plutonium dioxide powder is blended with depleted uranium oxide, the leftover material from uranium enrichment plants, at a ratio of roughly 7% to 10% plutonium. The mixture is ground together, pressed under hydraulic force into small cylindrical pellets, and loaded into industrial sintering furnaces running at extreme temperatures. The heat fuses the two oxides into a single, dense, stable ceramic material. These are mixed oxide fuel pellets, MOX fuel, and they are functionally equivalent to enriched uranium pellets, capable of powering the same reactors. The finished pellets are loaded into corrosion-resistant metal tubes, sealed by automated welding, and bundled into fuel assemblies identical in structure to standard uranium assemblies. Today, 44 reactors across Europe and Japan use MOX fuel, including 22 in France alone. The world's foremost reprocessing facility at Le Hague in Normandy handles over 1,000 metric tons of spent fuel every year and has produced more than 3,100 tons of MOX fuel since operations began. A single MOX fuel assembly produces enough electricity to power all the lighting for a city of 100,000 people for an entire year. And the stockpile of separated civilian plutonium worldwide now totals approximately 379 tons, enough, if fully recycled, to generate hundreds of billions of kilowatt-hours of clean electricity without mining a single additional gram of uranium from the Earth. The element that Glenn Seaborg first synthesized in a quantity too small to see, born from a cyclotron on a February night in 1941, now quietly powers millions of homes across the planet. That's the story of plutonium. If you found this fascinating, drop a like, share it with someone who'd never guess how their electricity is made, and subscribe so you never miss a new story. We'll see you in the next one, right here on Stories Behind Everything.